Hey guys, just wanted to say, welcome, and I put up the warm up, so uh, yeah, we'll work on it for 5 or 6 minutes, and then I'll go over it. Hey, all right. So let's see. So the first little bit of this of just showing the radius of convergence should be, routine by now. So right, if you look at if you do the root test, well, or if you do like, so an is like 1 over n squared 2 to the n. So absolute value of an to the 1 over n just converges to 1/2, right? So the radius of convergence is 1 over 1/2, which is 2. Okay, so that much should be hopefully pretty straightforward. Now, to show that it converges uniformly on the closed interval -2 to 2, what can we use? I mean, it's not too hard to do this, just sort of like from the definition of uniform convergence, but there's actually something that will make this very short. So what like one theorem should we use to solve this?
M-test?
Yeah, exactly. Yeah. So the Weierstrass M-test will actually work for the entire interval in this case, right? Because for all x in -2 to 2, we have, like, okay, hold on. Right. If we set gn of x to be like x to the n over n squared 2 to the n, then for all x in -2 to 2, we have that the absolute value of gn of x, which is just, 1 over n squared times the absolute value of x over 2 to the n, to the n, is, so this is less than or equal to 1, right? This is less than or equal to 1 over n squared. So if mn is 1 over n squared, then the sum of mn converges, and gn is less than or equal to mn on s, right? If s is this interval, right? So the M-test tells us that the convergence is uniform. And that's just it, right? You don't even have to muck around with like first showing that it converges pointwise on, like, you don't even have to test the endpoints. You just have to calculate the radius of convergence, and then the M-test automatically gives you that the series not only converges pointwise on the entire interval, but that it actually converges uniformly on the entire interval. So it's actually not too bad. Any questions about that? Okay. Yeah, great. I thought it was a relatively straightforward exercise, and it's just, applying the M-test. So let's see. I think one little thing I wanted to get out of the way is I actually wanted to just address the thing I was saying at the very end of yesterday's discussion, because I was talking about, like, so from yesterday, we were trying to show that if Fn goes to F uniformly on AB, and each Fn is uniformly continuous, then F is also uniformly continuous, right? That was the the last exercise yesterday. And so I had that sort of alternative idea, right? And so I was thinking about it from the solution, right? Alternative to the actual solution that we ended up with, which was suggested by the hint in the book. So I was saying, like, maybe there's an approach where you first say we can extend each fn to fn tilde on a, b, the closed interval, right? And then there's a little bit more stuff you have to do after that. And I think the way I described how you'd proceed from this point was a little bit muddled. So I just wanted to like clear it up a little bit. So like all we would have to do is show that the limit as x approaches a from above of f of x exists. Okay. Like in general, this would be enough. Okay, because all we're trying to do, and because like similarly, right? Similarly, the limit as x approaches b from below of f of x exists. As long as these two one-sided limits even exist at all, like you don't even have to like actually say anything. If you show in any valid way that these two limits exist, that's enough to show that f is uniformly continuous, right? Because that's all we're actually trying to do, is show that f itself is uniformly continuous. If you show that these two limits exist, that's showing that you can extend f to the closed interval, right? So this shows f can be extended. So, and if f can be extended continuously, then, you know, it's automatically uniformly continuous. So it would be enough just to show that these two limits exist. And so basically, you know, my idea was that maybe somehow you can show that. So maybe we could show that somehow the limit as x approaches a from above of f of x equals the limit as n approaches infinity of fn tilde of a, right? But or, you know, or something. Like, I don't know, I didn't have a super concrete plan. I think this was the idea I had in my head, but I think there are actually other possible things you could do too. Like, instead of even showing that these one-sided limits exist at all, you might just be able to show that the extensions themselves converge uniformly. Like, if you just show, like, another thing you could do, just show that fn tilde converges uniformly on AB, which I think should actually be like, this I think might not be too bad, but in the end, either route might require the same epsilon over 3 argument. So I'm not actually sure that either one of these is like easier than the solution that the book hinted at. I'm just trying to show you, honestly, like whether or not this is easier isn't even really like my focus anyway. My point is just that like it's healthy to consider these other ideas, because that will reinforce your knowledge of the material and your understanding of like the connections between the different concepts that we're covering, basically. Okay, so I do think that this is still very worthwhile to think about for you guys, because I do like definitely believe that, you know, the whole like continuous extension concept is it's like a really useful criterion for talking about like uniformly continuous functions on open intervals, I guess. Yeah. Anyway, I think that's all I want to say about this for now. Yeah. I think this. Oh yeah, go ahead.
Sorry, just to clarify, like the idea behind that is like if it's if it has a limit on a closed interval, then it's automatically uniformly continuous. So f is uniformly continuous if you restrict it down to AB. Is that what the idea behind that approach? This approach is?
This here.
Yeah.
Yeah. So this would be like, okay, if you could actually show this. So if Fn extension, if the extensions converge uniformly, that means that the limit, call it G, is continuous on AB, right? But G restricted to the open interval AB is just F, clearly, right? Or yeah, is the original F, right? So then G is an extension of F, basically. G is an extension of F. Yeah. Yeah, actually, the more I think about it, I think this would actually be the way you'd want to go. I think this one is bad. Probably bad. I mean, not that you couldn't do it, it's just like annoying. But this way, I think this way might be the simplest out of like, I mean, if you're focused on using extensions like this. Yeah. So the idea is it's just like, this is just a new sequence of functions, right? So anytime you have a sequence of continuous functions that converge uniformly, their limit, whatever it might be, right? So let's like, if we forget that we even knew about the function f in the first place, f tilde, if they converge uniformly, they have some limit function. So I'm just calling that g. And it's automatically continuous on this interval, right? It's continuous on the set where the convergence is uniform, which is the closed interval AB. But if G is continuous on the closed interval AB, then G is uniformly continuous, right? But then its restriction is also uniformly continuous, right? Or in other words, it's an extension of the original function we were talking about, right? F, the limit on the open interval. And like the reason it has to be, the reason the restriction has to be F is just because if Fn tilde converges uniformly, it still converges pointwise, right? It converges pointwise to G also. And if you look at the pointwise limits of Fn tilde for any value of X that isn't A or B, it's going to be the same thing as the pointwise limit of the original Fn's without the tilde, right? So that's why G of X equals F of X on AB, because of the pointwise convergence. Okay. So yeah, anyway. So then G would be an extension. Yeah, I think this is actually worth fleshing out maybe. But I don't want to spend too much more time on it today just because, yeah, it's leftover from yesterday. So any other questions though?
I have a general question about the recent lecture.
Yeah.
Just that you know how we have the series of x to the k over 1 plus x to the k, and we found that it's continuous on 0 to 1, the half open interval. Does that mean it's also uniformly Cauchy on 0 to 1, the half open interval?
No, because no, because that would require that the convergence was uniform. So the convergence is not uniform on 0, 1. So it can't be.
Not?
No, it's not.
Discontinuous. Okay.
Well, yeah, it's actually not because it's discontinuous. I think it actually is continuous. Like the function, I mean, the function is continuous, but it's because it diverges, like the limit of the function itself. Like if this is f of x, right, then the limit as x approaches 1 of f of x from the left is like infinity. Um, so like in principle, basically like uh, if fn is like the nth partial sum, then
Oh yeah, I see how it's not uniformly convergent because
like
it keeps on. Yeah.
yeah, fn is bounded for each n. So the fact, so this combined with this means that the convergence can't be uniform. At least that's one way of seeing it. The other way of seeing it actually is just that like um, the supremum of like x to the k over 1 plus x to the k over like x and 0, 1 equals 1/2, which doesn't converge to 0, right? That was the very last thing I talked about in the lecture, which was that like in order for a series of functions to converge uniformly on a set, that requires that the limit as like k goes to infinity of the supremum, this doesn't converge to 0 as k goes to infinity, I mean, of like the absolute value of g of x, gk of x for x in S is 0, right? This is kind of like, this is analogous to the theorem that like if a series of numbers converges, that means that an goes to 0 as n goes to infinity, right? So this is kind of like the analogy for a series of functions where it's like, of course, like if you fix your attention, if the series of gk of x converges as a series of numbers, if you like fix a value of x, right, and then just take the series of gk of x, if that converges, then clearly gk of x has to go to 0 just by this fact. But we're saying like something stronger than that, which is that like actually the biggest, quote unquote, biggest value of gk of x for each k, right, which might be happening kind of at different x's. I mean, even though this might not be achieved, right, the places in S where gk of x approaches this upper bound might be totally different for different k's, but they still, overall, these like least upper bounds on gk have to go to 0, basically. So the fact that the least upper bounds on these gk's are just constant at 1/2 means that the convergence automatically can't be uniform. Okay. That was a good question, by the way. Thank you. So any other questions? Okay. Let's see. So I was thinking the next thing it might be good to look at would be, I was actually thinking, this is actually from the previous section's problems, but I think it's actually a pretty good problem. So So show that you can basically show that you can take like this sort of diagonal limit where you're not only letting xn like change, but fn is also changing at the same time. Oops. Yeah. So yeah, I think this is a worthwhile lecture or exercise. And yeah, so let's say we'll resume at like 5:48. All right, I'll make a room for you guys to work in. Hey, all right. So let's see. How did you guys approach this? What am I doing? Solution.
From the continuity, I guess, of each, first, I guess the continuity of f itself, you can set delta to x minus xn, and then f of x minus f of xn is less than epsilon over 2. And then from the continuity of each fn, you can set, again, delta xn minus x, f to xn minus x, and then fn of xn minus fn of x is also less than epsilon over 2. And then you can stick that in a triangle inequality for f of x minus fn of x. And then, add the two epsilon over 2's together to get epsilon. And then,
Yeah, I think that's like, I think that's pretty close. I'm not sure it works perfectly. So hold on. Well, for one thing, okay, right. We shouldn't say we don't want to be saying like we're setting delta equal to xn minus x. It's more like we want to choose delta, right? So it's like, okay, we'll let epsilon be greater than 0. Choose a delta, right? Such that, and then what? What's our criterion for delta? I guess from what you were saying, it sounds like you want to make it so that if xn minus x is less than delta, then f of xn minus f of x is
less than epsilon over 2.
Less than epsilon over 2. Right. Okay. Yeah. Or really, like, it's just like, this could actually just be like any y, but then it'll apply to like xn. And not that it really matters, but yeah. Then like clearly for xn minus x less than delta, we have f of xn minus f of x less than epsilon over 2. Okay, right? And then what?
I guess do the same thing for fn.
Okay, so we'd be choosing like a different delta in that case.
Yeah, so then I guess
right.
use minimum delta, like have it, is it min or max delta?
Yeah, although, so then it's like, okay, if you're choosing it for fn, then it's kind of like you're fixing a value of n, because if you choose a delta for every single fn, then you can't actually take the minimum of all of the deltas, because there'll be an infinite number of deltas.
Oh yeah.
So if you fix a specific value of n, and I think so, okay. I think you're on the right track. I think you just haven't quite like organized all the different pieces in quite the right way, and I'm not actually sure that this is going to end up. I think if you mess around with this enough, you'll get it to work. I'm going to try to like show you what I have in mind, which is basically, I think, the same thing, but just like after you kind of organize the ideas. So, and I know you only had like 10 minutes to work on it, so whatever. But actually, I think in the end, I think this actually boils down to a version of the epsilon over 3 argument. So I don't think you can do it with just 2 things. I think you have to use you have to use like 3 terms in a triangle inequality. So I think in this case, it kind of helps to like write down. So what we're trying to do is like, well, for one thing, we want to think about what we want in the end, right? We want this to be, so we want this to be less than epsilon for n greater than some n we pick, right? That's what we want in the end. And so then it's like, what you want to do is think about what you can do with this expression. And I think what makes, I think at least what comes to my mind is like, do this. So it's like Okay. So this is less than or equal to like fn of xn minus like fn of x plus, and then like fn of x minus, oh wait, maybe it is just epsilon over 2. Because, yeah, so this is what you were going for, actually. Right. Okay, so then it's like you have to like, but now it's like we have to organize the order in which we kind of pick these things, right? Because basically it's like, okay, for this one, we need to make sure that n is big enough that fn is like close to f, right? So is this right? Is this gonna work? Yeah, I think so I think first pick n such that, oh yeah, okay, I see, right. So I think we're going to end up picking multiple n's, not like multiple deltas, actually.
So you can just go from a sequence from an approach of sequences rather than like epsilon delta stuff.
Yeah. Because
Okay.
it's like in the end we're dealing with a sequence. Yeah, I think that's kind of where things are getting a little bit muddied up. Yeah. So if you pick n1 such that like f, so they converge uniformly, so we can just say like, okay, fn of like y minus f of y is less than epsilon over 2 for all y in this, and for all n greater than n1. And then also pick, okay, oh, right. Oh no, maybe it is actually an epsilon over 3. Because I think what you want to do is after you do this, then you can like, okay, what the real inequality we want is actually like, okay, I feel like, wait, hold on. We had fn of xn minus fn of x. So how do we make sure that this is?
Because we had to use a continuity of each fn. That's what I was thinking.
Right. But I we deleted the n in the wrong place. Hold on. You actually want, okay. Yeah. We want like f of xn here. And then this will be like, yeah. Oh man. Okay. Yeah, this will be f of xn and then f of x. Hey man. Right. So now this is still what we want. Okay, good. And then pick n2 such that for all n greater than n2, we have f of xn minus f of x is less than, so this can be epsilon over 2 now. Man, sneaky. That was very sneaky. Okay, epsilon over 2. And then pick n to be like the max of those. I'm pretty sure this is all good now. Because then for little n bigger than this capital N, this will definitely be, hold on, is that right? Yeah, this has to be less than epsilon over 2 because of how we picked capital N1. And this is less than epsilon over 2 because of how we picked capital N2. Am I missing anything? I think this works. Yeah. So the real problem, okay, the reason we had to do it this specific way and not like fn of x here and have fn of x here is because we want to be like effectively picking only one delta. So there's like an implicit delta that we're picking, right? Because when we pick n2 here, right, to make this happen, what I'm really using, okay, let me go to a new page. So when we pick n2 such that f of xn minus f of x is less than epsilon over 2, right? For all n greater than n2. What we're really doing is picking delta such that absolute value of f of y minus f of x, right, is less than epsilon over 2 for y such that y minus x is less than delta, then picking n2 such that absolute value of xn minus x is less than delta for n greater than n2, right? So the thing is, there's a delta associated with the function f itself, right? This delta like corresponds to the limiting function f. So when we had it the other way, right? Let's see. So the other way we were looking at was like having fn of x here and then having fn of x here, right? Then it's like, then what you're doing is you're invoking the continuity of like each individual fn, but then that would require you to basically be choosing like infinitely many deltas, right? That's like the problem, is that you don't want to be directly accessing the continuity of each fn like at the same time, because you can't take like the smallest delta out of all of those. So that's why you have to use the limiting function. But the thing is, like, the limiting function, we know it's continuous because we know that continuous functions converge uniformly to continuous functions, basically, right? So like we are implicitly using the continuity of fn, right, when we say that this is possible, basically. So, okay, hold on. Let me go back to what we had before. So this, and then.
Yeah, that makes more sense.
Yeah. It's like, sometimes you just miss that you can even like, that you even have like a choice of like which end to take away in the intermediate thing, right? Like it definitely took me a second to remember that there's like an alternative there. So yeah, it's like over here, this is only possible since f is continuous, which is only because each fn is continuous and the convergence is uniform, right? So we are like implicitly relying on the continuity of all the fn's when we do this. It's just that we don't want to use it like directly. Yeah. Anyway, yeah, I actually think that ended up being a really nice problem. I'm kind of glad that I didn't like work out the solution too carefully beforehand, because I think it was kind of a good moment, you know, to show the thought process behind some of this stuff and to kind of like dissect the solution a little bit. You know, I think this is kind of a nice like discussion to have about like, you know, how does the logic really work? And, you know, yeah, I don't know. I think hopefully it helps deepen your intuition and understanding for the concepts. So anyway, yeah, I think that's going to be it for today. Any last minute questions? There's going to be a review session on Monday again, so it's going to be the same like setup and pattern as like the first midterm. It's going to be review on Monday, and then I'll post the midterm at midnight, and it'll be like a 24-hour deal.
Would knowing function spaces and just like having a solid understanding of that like be useful for the midterm?
Um, mm, I would say focus on the basics first. Yeah.
Okay.
Like it's not like it could help you possibly like because if you do learn about that stuff, then it kind of gives you like a higher perspective on the material, which then might actually help like guide your instincts in solving like the more like elementary problems. But it's like I don't think I don't really plan on like putting in problems that are like specifically going hard on like the function space angle really.
Is there a
Like
functional analysis class at Berkeley?
oh man, I think I got this question last time I taught this class, and like if I remember correctly, it's only like graduate level. I don't think there's any undergrad level functional analysis classes, unfortunately,
Okay.
at least from what I remember. But I think there is. I mean, there should be a graduate functional analysis class, obviously.
Hmm.
I just yeah, I don't know. I don't know what it's like. I took functional analysis at my undergrad,
Oh.
so yeah, that was a long time ago, and it was a very different environment. Yeah,
Hmm.
I took it from Richard Melrose actually, who's
Oh.
kind of a luminary in the field. Yeah, pretty cool. Um, it's a great subject. I wish I had devoted myself more to it at the time. I was doing like when I took that class, I did every homework like the night before it was due, and I just honestly like yeah, I don't know. I didn't absorb it as well as I could have, and I kind of regret that a little bit. But you know, oh well. C'est la vie. Anyway, other questions? So yeah, I mean, I think the extent to which there'll be like functional analysis oriented subject like material on the exams, it's gonna focus on like the main definitions we've made about uniform convergence and like um, the theorems, like just the theorems about uniformly convergent sequences of functions, basically, like all the actual main theorems from sections like 24 and 25. Uh, that's yeah. So all of that stuff can be phrased without reference to function spaces, basically, is what I'm saying. So what all of I'll kind of anything that could be like a function space problem will probably be phrased as like just a problem about uniformly convergent sequences of functions or something like that. Yeah, roughly speaking. All right. Okay, so I'm going to call it then. So I'll see you guys next week. Well, I have office hours tomorrow too. So yeah.
Thank you.
Thank you.
Yep. See you later.
Thank you.